June 15, 1944, England. Dearest Sarah, you asked what I did when the bomb site was destroyed. Here's the answer. March 8, 1944. Flak hit us over Frankfurt. The Norden bomb site, the most sophisticated bombing computer ever built, $10,000 per unit, America's most classified military technology, was completely destroyed. We had one chance to hit the target, a ball-bearing factory, critical German war production. Intelligence said this factory alone supplied bearings for 500 tanks per month. We couldn't come back tomorrow. Weather window closing, enemy fighters responding. This was our only shot. And I had no bomb sight. What I did have, 18 new bullet holes in our aircraft, and a physics degree from Northwestern. I realized those bullet holes were unintentionally perfect. Different positions along the fuselage, different altitudes within the aircraft, different angles. Wind was flowing through them. Each hole was experiencing different air pressure. I could hear the whistle, different tones from each hole, different flow rates. That's fluid dynamics. Air pressure differential indicates wind speed. Flow direction indicates wind angle. Multiple measurement points allow triangulation. The bullet holes were an improvised anemometer array. I spent 20 minutes calculating wind speed from pressure differential, wind direction from flow vectors, triangulated exact wind conditions at our altitude, manually calculated bomb trajectory compensating for that wind, release bombs at my calculated point, direct hit. Ball-bearing factory destroyed. The $10,000 bomb site couldn't have done it better. Let me tell you the whole story, from the beginning, so you understand how your husband used physics education to complete an impossible mission. I'm First Lieutenant James Chen, Bombardier, 381 Bombardment Group, B-17 Flying Fortress. Sarah's Promise, named after you, of course. You remember when we met at Northwestern in 1940? You were studying literature. I was studying physics. You asked why a future bombardier needed to understand fluid dynamics and differential equations. I said, because bombing isn't just dropping things. It's physics, trajectory, air resistance, wind compensation. I need to understand the principles, not just follow procedures. You smiled and said, my practical physicist. March 8, 1944, you learned exactly how practical physics could be. The mission briefing was clear. Frankfurt ball-bearing factory. Primary target, heavily defended, expect flak, expect fighters. But destroy this factory and we disrupt German tank production for months. Ball bearings are critical, Sarah. Every tank needs dozens of precision bearings. Every aircraft needs hundreds. Ships, trucks, artillery, all dependent on high-quality bearings. Germany has limited bearing production capacity. This factory alone produced bearings for approximately 500 tanks per month. Intelligence said, this target is worth the casualties. It must be destroyed. We took off at 0800 hours, 36 B-17, full bomb load. Fighter escort for part of the route, standard heavy bomber mission. Everything was routine until we reached Frankfurt. The flak was intense. German anti-aircraft batteries knew we were coming. They'd positioned guns around every strategic target. When we began our bomb run, the sky turned black with exploding shells. Our pilot, Captain Morrison, kept the aircraft steady. Steady on bomb run! Bombardier, you have control. I was in the nose, looking through the Norden bomb site, adjusting for wind, calculating trajectory. The bomb site was doing its job, computing wind compensation, adjusting for altitude and airspeed, calculating the precise release point. Then the flak hit us. One shell exploded close, maybe 50 feet from our nose. Shrapnel tore through the fuselage. I heard metal ripping. felt the aircraft shudder, heard the crew shouting damage reports over the intercom, and I watched the Norden bomb site spark, smoke, and die. Just stopped working. The gyroscopes froze, the computing mechanism jammed, the mirrors cracked. $10,000 of precision bombing technology destroyed in 1 second. I keyed the intercom. Pilot, bombardier, bomb site destroyed, unable to complete bomb run. Morrison responded immediately. Can you repair it? Negative, complete destruction. Shrapnel through the computing mechanism. Recommend we abort? Return to base with bombs still loaded? I looked out the nose, looked at the factory below, looked at the target we'd flown 400 miles to destroy. The target that was producing bearings for 500 German tanks every month. The target we might not get another chance to hit. And I heard whistling, 18 different pitches, 18 different tones, wind flowing through 18 new bullet holes in our fuselage. Negative, I said. I can still hit the target. How? Your bomb site is destroyed. I'll calculate it manually, using the bullet holes. Silence on the intercom. Then Morrison. Say again? The flak created 18 bullet holes at different positions. Wind is flowing through them at different rates. I can measure pressure differential and calculate wind speed and direction. Can manually compute bomb trajectory. More silence. Then Morrison. Chen, are you sure about this? Yes, sir. It's fluid dynamics, physics. I can do this. We have one bomb run, one chance. If you're wrong, we wasted this entire mission. I'm not wrong, sir. Physics doesn't guess. It calculates. Morrison made his decision. You have control, Bombardier. We're trusting you. 20 minutes. That's what I had. 20 minutes until we'd reach the release point. 20 minutes to do manually what the Norden bomb site did automatically. But I wasn't doing it the same way the bomb site did. I was doing it better, because I understood the principles, not just the procedures. First step, inventory the damage, count the bullet holes, note their positions. I moved through the nose section, 18 holes total. Here's what I found. 3 holes near the bombardier position, forward fuselage, approximately 5 feet above the aircraft floor. Sizes 1 inch, 2 inches, and 3 inches diameter. 5 holes in the mid-fuselage. Around the waist gunner positions, approximately 8 feet above the floor. Sizes 1 to 4 inches. 7 holes near the tail section. Various positions, approximately 6 feet above the floor. Sizes 1 to 5 inches. 3 holes in the roof section. Near the top turret, approximately 12 feet above the floor. Sizes 2 inches each. 18 holes. Different positions, different altitudes within the aircraft, different sizes, different angles to the wind, and wind was flowing through all of them. I could hear it, whistling, each hole producing a different pitch based on its size and the wind speed flowing through it. That's when I knew this would work. Sarah, remember when I explained Bernoulli's principle to you? How faster moving air creates lower pressure. How pressure differential indicates velocity. That's what I was hearing. Each bullet hole was measuring air pressure at its specific location. The whistle pitch indicated flow rate. The tone quality indicated turbulence. The volume indicated pressure differential. Each hole was an independent pressure sensor. 18 sensors at different positions. That's an improvised anemometer array. Step 2. Acoustic analysis. Listen to each hole carefully. Estimate the flow rate from the whistle pitch. The 3 holes near my position. High pitch whistles. Fast flow. Wind was hitting these directly. They faced into our direction of travel. The mid-fuselage holes. Lower pitch. Moderate flow. Wind was hitting at an angle. The tail holes, mixed pitches, some high, some low. Wind was turbulent here, wake from the forward fuselage affecting flow. The roof holes, very high pitch, fastest flow. These were highest altitude, catching the wind with minimal aircraft interference. I could hear the gradient, could hear how wind speed changed with position, could hear the three-dimensional wind profile around our aircraft. That's data, that's measurable, that's physics. Step 3, calculate pressure differential. Convert acoustic observations to wind speed estimates. I knew the physics. Whistle pitch correlates to flow velocity. The higher the pitch, the faster the flow. The faster the flow, the greater the pressure differential. I estimated flow rates. Nose holes, approximately 140 miles per hour flow, high pitch. Mid-fuselage, approximately 110 miles per hour flow, moderate pitch. Tail holes, 80 to 120 miles per hour flow, variable, turbulent. Roof holes, approximately 150 miles per hour flow, highest pitch. But our aircraft was flying at 180 miles per hour. So why were flow rates different at different positions? Because of wind. External wind was adding to or subtracting from our airspeed, depending on hole position and wind direction. The nose holes facing forward. If they showed 140 miles per hour flow and we're flying 180 miles per hour, that means we have a 40 mile per hour headwind. The roof holes showing 150 miles per hour. They're higher altitude, catching stronger wind. Wind speed increases with altitude. The mid-fuselage holes showing 110 miles per hour. They're at angle to wind, measuring crosswind component. I was building a three-dimensional picture of wind conditions, not just how fast, but from what direction, and how does it change with altitude? Step 4. Wind gradient extrapolation. This was critical, Sarah. This is where physics education made the difference. The holes in the aircraft ranged from 5 feet above the floor, nose section, to 12 feet, roof. 7 feet of altitude difference, and I could hear the wind speed difference between them. Could hear that the roof holes had faster flow than the nose holes. That's wind gradient. Wind speed increases with altitude. Even within the aircraft, I could measure it. The 7-foot altitude difference showed approximately 10 miles per hour wind speed increase. Now I could extrapolate. If wind speed increases 10 miles per hour per 7 feet of altitude, what's the wind speed at bombing altitude? We were flying at 22,000 feet. The bombs would travel through air from 22,000 feet down to ground level. I needed to know the wind at the altitude where bombs would spend most of their travel time, approximately 15,000 feet average. Using the gradient I measured in the aircraft, I calculated wind conditions at bombing altitude. Wind speed, approximately 65 miles per hour, stronger than ground-level wind. Wind direction, from west-northwest, calculated from pressure differential across fuselage. Crosswind component affecting bomb trajectory, approximately 45 miles per hour perpendicular to our flight path. That's the wind my bombs would experience. That's what I needed to compensate for. Step 5, trajectory calculation. Manual computation of bomb release point. I knew our current conditions. Our altitude, 22,000 feet. Airspeed, 180 miles per hour. Heading, 087 degrees, almost due east. Target, 8 miles ahead, slightly north of our track. I knew the bomb ballistics, memorized tables from training. 2,000-pound bombs. Terminal velocity, approximately 550 miles per hour. Flight time from 22,000 feet, approximately 50 seconds. Trajectory, ballistic curve affected by gravity and wind. I knew the wind, calculated from bullet holes. 65 miles per hour from west-northwest. Crosswind component, 45 miles per hour, pushing bombs north. Now I calculated, in 50 seconds of flight time, 45 miles per hour, crosswind will push bombs approximately 3,300 feet north of the straight-down trajectory. So I needed to release bombs 3,300 feet south of the target. Aim south, let wind push them north, bombs hit target. I also calculated the forward distance. Bombs travel forward at our airspeed, 180 miles per hour, plus acceleration from wind. They'd travel approximately 2.5 miles forward during the 50-second drop. Release point, 2.5 miles before target, 3,300 feet south of target line. I calculated the exact compass bearing, 085 degrees. Release when that bearing intersects the target. All of this in 20 minutes, using bullet holes, physics knowledge, and mental calculation. Morrison's voice on the intercom. Bombardier, we're approaching release window. Do you have a solution? Affirmative. I have release point calculated, adjusting for wind compensation based on bullet hole pressure measurements. And you're confident in this calculation? Yes, sir. Physics is consistent. I've measured wind, calculated trajectory, determined release point. It will work. Then you have control. Take us to the target. I guided Morrison. Pilot, come left to heading 085. We need to offset south of target to compensate for crosswind. Coming left to 085. Steady on that heading, 2 minutes to release. I watched through the nose, watched the target approaching, watched my calculated release point getting closer, 1 minute. I could still hear the bullet holes whistling, could still hear the wind, could verify my calculations orally. The pitch hadn't changed, meaning wind conditions were stable. 30 seconds. The crew was silent. Everyone knew this was manual bombing, no bomb sight, just physics and bullet holes. They were trusting my calculation. 15 seconds. I put my hand on the bomb release lever, watched the target, waited for the exact moment when bearing and distance intersected my calculated release point. 5 seconds. Almost there. Bombs away. I released all bombs. Felt the aircraft jump upward as 2,000 pounds of explosives dropped free. Watched the bombs fall away below us. Now, we waited. 50 seconds. That's how long bombs take to fall 22,000 feet. Sarah, those 50 seconds felt like 50 hours. I watched the bombs fall, watched them drift north, exactly as I'd calculated. The crosswind was pushing them. The trajectory was perfect. Morrison climbed us away from the target. Standard procedure after bomb release: get away from flak. The bombardier from the aircraft behind us on the intercom. Chen, I have your bombs in sight. Tracking. They're right on target. Direct hit. The factory is gone. Perfect bombing run. The crew erupted, cheering, shouting, celebrating. Morrison, outstanding work, Bombardier. I don't know how you did that, but you just proved physics beats technology. I sat in the nose, hands shaking, not from fear, from the realization of what had just happened. I'd replaced a $10,000 precision bombing computer with 18 bullet holes and physics education. I'd calculated wind speed and direction from acoustic properties of battle damage. I'd manually computed a bomb trajectory that hit the target perfectly. American education had prepared me. American ingenuity had applied it. American physics had won. When we landed back in England, the intelligence officer was waiting for us. Lieutenant Chen, photo reconnaissance confirms direct hit on the ball-bearing factory. Primary production building destroyed. Secondary buildings damaged. Estimated production loss: 6 months minimum. 6 months. That factory wouldn't produce bearings for 3,000 German tanks. Because of physics. Because I understood how air flows through holes. Because I could calculate pressure differentials and wind gradients. The intelligence officer continued. How did you achieve this accuracy without a functioning bomb sight? I explained. The bullet holes, the fluid dynamics, the acoustic analysis, the wind calculation, the manual trajectory computation. He stared at me. You used battle damage as scientific instruments? Yes, sir. Each hole was measuring air pressure at its position. Multiple measurement points allowed triangulation of wind conditions. From there, trajectory calculation was straightforward. I've never heard of anything like that. It's physics, sir. Bernoulli's principle, wind gradient theory, ballistic trajectory calculation, everything they taught me at Northwestern. He wrote his report. Bombardier demonstrated exceptional innovation and technical skill, achieved precision bombing accuracy using improvised wind measurement technique. Recommend for commendation. The story spread through the base. Other bombardiers wanted to know how I did it. I explained the physics, showed them the holes in our aircraft, demonstrated the acoustic analysis technique. Some got it, understood the fluid dynamics, started paying more attention to how wind sounds, how pressure differentials manifest, how physics governs everything in aerial combat. Others didn't. They wanted to follow procedures, wanted their Norden bomb sites functioning properly, couldn't imagine improvising scientific measurements from battle damage. That's the difference between understanding and following, Sarah, between knowing why things work and just knowing how to operate them. American military trains us to understand, to think, to innovate when standard procedures fail. That's our advantage. German bombardiers were excellent technicians, could operate their bomb sites perfectly. But if their equipment failed, they'd abort. They'd return to base. They couldn't improvise. We can. Because American education teaches principles, not just procedures. Teaches us to think scientifically, not just follow instructions. Sarah, I know this letter is technical. I know I'm explaining physics and fluid dynamics when you just wanted to know I'm safe. But I need you to understand something. The education you encouraged me to pursue, the physics degree you supported, even when I could have just gone straight to military training, that education saved our mission, saved our crew, contributed to winning this war. When we met at Northwestern, you asked why I studied physics. You said, "Can't the military just teach you what you need to know?" I said, "The military can teach me procedures, but understanding the principles, that's what university teaches. That's what makes me not just a technician, but an engineer, someone who can solve problems that don't have procedures yet." March 8th, 1944, I faced a problem with no procedure. The Norden bomb site manual doesn't have a chapter on alternative bombing techniques using battle damage. There's no training course on acoustic analysis of wind flow through bullet holes. I had to create the solution, had to apply physics principles to an unprecedented situation, had to trust that understanding the science would lead to the right answer. And it did. Because physics works, because fluid dynamics is consistent, because American education gave me the tools to think through problems. You asked in your last letter if I'm being careful, if I'm taking unnecessary risks. Sarah, I promise you, I'm being as careful as this war allows. I'm not taking foolish risks. I'm not being reckless. But I am using everything I learned to complete our missions. I'm applying every bit of physics education. I'm innovating when necessary. I'm thinking through problems. That's not reckless. That's competence. That's what American education created. Soldiers who can think, not just follow orders. The pilots trust me. The crew trusts me. They know I'll get bombs on target. They know I understand the science. They know I won't guess. I'll calculate. That trust means everything. In a bomber crew, everyone depends on everyone else. The pilot depends on me to hit targets. I depend on the pilot to keep us steady on the bomb run. The gunners depend on the navigator. The navigator depends on the radio operator. We're a team. And our team is effective because American military builds teams of thinkers, not just followers. I have 12 more missions to complete, 12 more targets to hit. Then my tour is done and I can come home to you. I'll complete those missions, I'll hit those targets, and I'll use everything I learned, every bit of physics, every principle of fluid dynamics, every mathematical technique to ensure success. Because that's what American bombardiers do. We don't just drop bombs. We apply science. We calculate trajectories. We understand the physics of flight and explosion and destruction. We're not just warriors. We're engineers, scientists, mathematicians, armed with knowledge and education. That's America's advantage, Sarah. Not just our industry or our numbers or our resources, our education. Our system that teaches people to think scientifically, to understand principles, to innovate. Germany has excellent engineers, excellent scientists, but their military is rigid, follows procedures, doesn't encourage innovation at lower ranks. American military says, you're educated, you understand the principles. When procedures fail, use your knowledge, figure it out. That's why we're winning. I miss you terribly. Miss our conversations about physics and literature. Miss explaining science to you while you explain poetry to me. Miss our different perspectives on the world. But I'm grateful for those conversations. Grateful that you made me explain things clearly. Grateful that you asked why and how instead of just accepting what I said. Teaching you physics made me understand it better. Made me think through the principles clearly. Made me able to explain fluid dynamics to bomber crews who need to understand how wind affects their aircraft. So thank you. Thank you for being curious. Thank you for asking questions. Thank you for making me a better physicist by making me a better teacher. And thank you for supporting my education, for encouraging me to study physics even when it seemed impractical, for believing that understanding principles matters more than just learning procedures. March 8, 1944. That support paid off. Your encouragement of my education contributed to destroying a factory that would have produced bearings for 3,000 German tanks. I couldn't have done it without the education you supported, without the understanding you helped me develop. 12 more missions, Sarah. Then, I'm coming home. I'll bring stories about physics in practice, about fluid dynamics at 22,000 feet, about acoustic analysis of bullet holes, about American ingenuity and education. But more than stories, I'll bring understanding. I'll bring proof that education matters, that physics isn't abstract theory. It's practical, life-saving knowledge, that American schools create the advantage that wins wars. And I'll bring myself home safely, because I understand the science that keeps bombers in the air, because I can calculate trajectories when equipment fails, because American education gave me the tools to survive. Stay safe. Stay strong. I'll see you soon. Your loving husband, First Lieutenant James Chen Bombardier, 381 Bombardment Group, United States Army Air Force P.S. Remember our wedding day? You said, my practical physicist. I said, your husband who turned science into solutions. March 8th proved both of us right. Physics is practical when you understand it deeply enough, and I'm yours, forever. P.P.S. The crew has started calling me Professor Chen. They say, I teach physics while dropping bombs. I told them, physics is the bomb. They groaned at the pun, but they trust the science. And that's what matters. Subscribe for more untold stories where American scientific education became American tactical advantage, where physics replaced expensive technology, where understanding principles defeated equipment failure, where university education created battlefield innovation. This is American education at war, not just following procedures, but thinking through problems, innovating solutions, and turning science into victory.